Welcome to the High Voltage AI Podcast. I'm Alex Reed, and after kicking off our FERC Order 1920 deep dive yesterday, laying out its foundational requirements, we're back today. And we're going to unpack something really transformative for you, our listener, the electric utility engineer, how we evaluate essential infrastructure projects.
That's right. FERC Order 1920 isn't just, tweaking the rules slightly. It's fundamentally reshaping how transmission projects get assessed. We're moving beyond that traditional kind of reliability-only planning to a much more comprehensive multi-benefit framework. This is a critical shift for everyone in the industry, and it's going to change how we build the grid.
Yeah, and this isn't just theory, right? Or some new spreadsheet exercise we all have to learn. Think about that American Electric Power example. They had a $400 million transmission line, initially rejected purely on the old reliability metrics. But then, once he included other benefits now required by FERC Order 1920, things like, production cost savings, capacity benefits, even state policy support.
Suddenly it pencils out.
Exactly. That project suddenly became economically justified. The total quantified benefits, they exceeded the cost by a remarkable 2.3 to 1. It turned what looked like a no-build into a priority project. Okay, let's unpack this, because this isn't some accounting trick. It's a fundamental shift in how we truly value these massive grid investments.
Precisely. And for you, an electric utility engineer, our mission today is really to equip you with a thorough understanding of these 7 distinct value categories, the ones mandated by FERC Order 1920. And crucially, what are their engineering implications? This deep dive should help you navigate this new landscape.
Okay, so let's dive into this big shift. For decades, transmission projects were primarily justified based on, just a few key reliability criteria. We look at N-1 contingency, the system's ability to serve projected peak demand that's load-serving capability maintaining acceptable voltage levels, and then a fairly simple economic evaluation comparing project costs versus basically outage costs.
Right, and that was the old world. Under FERC Order 1920, every single transmission project must now be evaluated across 7 distinct benefit categories. These are first, reliability benefits. Second, adjusted production cost benefits. Third is capacity benefits. Fourth, decreased transmission losses. Fifth, increased competition. Sixth, extreme weather and natural disaster recovery. And finally, seventh, state and federal policy goals.
Wow, 7. That's comprehensive.
It is. It fundamentally redefines what value means in grid planning. It pushes engineers like you to think beyond just the wires and poles, to think about the economic and societal impact of every decision. And this shift, it demands new analytical tools, much more data collection, and fundamentally different approaches to project economics.
Okay, let's start with the bedrock then. Reliability benefits. Reliability has always been paramount, obviously, but FERC Order 1920 significantly enhances how we evaluate it. It's moving beyond that traditional deterministic sort of pass or fail N-1 analysis. What's the biggest shift in how we're now asked to think about reliability?
Well, the big thing is moving to probabilistic assessment and risk-based reliability evaluation. Crucially, there's a strong emphasis now on customer impact analysis. This uses the value of loss load, or VOLL. And think about this. For residential customers, VOL might be, say, $3 to $15 per kilowatt hour. Depends on how long the power's out.
Okay.
But for commercial, it jumps maybe $15 to $50 per kilowatt hour. Industrial could be up to $500 per kilowatt hour. And then you get to data centers, where every second of downtime costs potentially millions. That VOL can be a staggering $1,000 to $10,000 per kilowatt hour. That's the real cost of unreliability laid bare.
That puts it in perspective.
Exactly. And we also now need to consider cascading analysis, sequential failure scenarios, and integrate climate resilience for reliability under extreme weather.
Right. This is where the numbers really start to tell a powerful story. Can you walk us through how even a small reliability improvement translates into long-term value? Like, imagine a transmission upgrade. It reduces load at risk by, say, 500 megawatts. If that upgrade has an annual outage probability of just 0.1% and an average duration of 4 hours, what does that look like?
Okay, so in that scenario, that translates directly to an annual reliability benefit of about $100,000. Now, project that over 20 years using a 7% net present value discount rate. That single improvement is worth $1.06 million in reliability benefits alone.
Just from preventing those specific outages, that's tangible.
Absolutely. It's a direct return on investment. But to achieve that level of precision, the new data requirements for reliability are pretty extensive. You need detailed historical outage data, a good understanding of load composition by customer mix, weather correlations for better forecasting, and robust cascading models. It means getting really granular with the data.
Okay, so reliability is critical, but it's also about the cost of generating the power in the first place. How is FERC Order 1920 changing how we account for production costs? Moving beyond just looking at, say, congestion relief.
It's a significant leap forward, really. The enhancements under FERC Order 1920 required these comprehensive 8,760-hour production cost simulations. And you have to consider multiple future scenarios for generation mix and load growth. It also mandates integrating storage technologies, batteries, pumped hydro, and variable resources like wind and solar.
Right, the variable stuff is key now.
Totally. And the key variables considered are much more detailed. Fuel costs for natural gas, coal, nuclear, variable O&M costs, startup costs for thermal plants, even emission costs like carbon pricing where applicable.
And the renewable integration benefits must be huge here. We're talking less renewable energy curtailment, right? Improved capacity factors for those resources.
Exactly, and enhanced system flexibility, better use of storage. It really changes the economic landscape for renewables integration.
So how do we actually crunch these numbers? What's the methodology?
Well, it boils down to a rigorous comparison. You look at the baseline production cost without the project. Then you compare that to the with project case. Analyze the annual savings. Crucially, you run multiple future scenarios to account for uncertainty, and then calculate the 20-year net present value of those savings.
Okay, give us an example. Let's say a project reduces annual production cost by $15 million. Maybe $8 million from less gas generation, $4 million from less renewable curtailment.
Yeah, maybe $2 million from better storage use, $1 million from reduced cycling costs, something like that.
Okay, so $15 million annual savings. What does that look like over 20 years?
With that $15 million annual saving, using our standard 7% discount rate over 20 years, you're looking at a net present value of about $159 million.
Wow. That's a massive economic win just from production cost saving.
It really can be.
Okay, and speaking of economic value, it's not just avoiding cost, but also generating new capacity. This is where we shift from just counting megawatts towards more sophisticated probabilistic assessments, isn't it?
That's absolutely right. FERC Order 1920 introduces enhancements like effective load carrying capability, or ELCC. ELCC gives you a statistical capacity value, not just a nameplate rating. It also emphasizes probabilistic resource adequacy assessment and integrating with markets to quantify the capacity market value. And we're now explicitly considering transmission-dependent generation resources, those resources whose capacity value really relies on that transmission line existing or being upgraded.
So how did that ELCC calculation work, roughly?
Well, you calculate the loss of load probability without the project. Then you recalculate it with the transmission enhancement. Then you figure out how much additional load the system can sustain at the same reliability level because of the project. And finally, you value that additional capability using the market capacity price.
Okay, that makes sense. And beyond just the direct megawatts added, there are bigger generation interconnection benefits too, right? Like enabling new resources.
Definitely. This means improved access for new resources, especially remote ones like large wind or solar farms. Enhanced delivery capability. It boosts resource diversity across the grid, which is good for reliability and economics. And ultimately, it can increase market competition by enabling more players.
It really changes the game for bringing new power online.
It does.
So another calculation example. Say a transmission project adds 300 megawatts of ELCC. What kind of value could that represent?
Okay, 300 megawatts ELCC. Depending on the market price for capacity, that could yield an annual capacity benefit of, let's say, $16.4 million. Over 20 years with that 7% NPV, you're looking at about $174 million in value.
Another big number. Okay, fourth category. Decreased transmission losses. This feels like an area often maybe underestimated in traditional planning.
I think that's fair to say. It was often simplified, but FERC Order 1920 mandates a much deeper dive than just simple I²R calculations.
Right, this is where it gets into the real engineering specifics, moving beyond those simpler formulas.
Precisely. The enhancements involve detailed AC power flow analysis with really comprehensive loss modeling. You need hourly loss calculations over the entire year, all 8,760 hours. And then you put an economic value on those saved megawatt hours based on market prices, typically the average locational marginal price, or LMP. The goal now is really system optimization, specifically for loss minimization.
What affects those losses?
Well, key factors include load distribution across the network, voltage levels, remember, higher voltages, reduce losses for the same power transfer, conductor selection is huge, and also reactive power management.
And this focus on losses really opens up opportunities for, advanced engineering solutions. What kind of innovations make a difference here? You mentioned conductors.
Yeah, absolutely. Advanced conductors like ACSS, that's aluminum conductor steel supported, can offer maybe 25 to 40% loss reduction compared to traditional ACSR. HTLS, high temperature low sag conductors, give you more capacity and lower losses. And ACCC, aluminum conductor composite core, can boast 25 to 30% lower resistance. These are real engineering choices with big impacts.
And voltage optimization.
Right. Things like optimal capacitor placement, using smart transformer taps for better control, and dynamic VAR support systems for real-time reactive power optimization. It's about squeezing more efficiency out of the existing and new system.
Okay. Moving on to number 5, increased competition. This feels like a less traditional benefit category for transmission planning. How does a transmission line actually foster market competition?
It's a fascinating area, and FERC Order 1920 brings some significant enhancements here, too. We now need to perform detailed market simulations, analyze generation unit commitment and dispatch patterns with and without the project. We need to quantify the potential reduction in market manipulation opportunities, and even look at how transmission can incentivize innovation through competition.
What are the metrics for that? How do you measure more competition?
Key metrics include price convergence, basically, seeing those locational marginal price differences shrink across the system. Also, increased supplier diversity, looking at market share analysis, and how easily new generation can enter the market because the transmission barrier is lowered. The quantification often boils down to summing up the product of the price reduction achieved times the load served in those areas.
And this requires pretty sophisticated market simulation tools, I imagine.
Oh, yes. You need models that can handle demand response, realistic generation bidding behavior, and accurately represent transmission constraints and how they impact market outcomes.
Okay, number 6, extreme weather and natural disaster recovery. This feels increasingly critical, doesn't it, given what we're seeing with climate change? It's about moving beyond just standard design criteria for, a normal Tuesday and thinking about the really bad days. How does the order address that?
It's absolutely crucial, and FERC Order 1920 is quite explicit. It enhances this area with mandatory climate resilience analysis, integrating future climate scenarios into planning. It pushes for enhanced design standards specifically for extreme weather resilience. There's a focus on system restoration capabilities, including things like black start capability, and it calls for enhanced emergency operating procedures.
How do you integrate climate data? That seems tricky.
It involves looking at 50-plus years of historical weather data, but also incorporating climate change projections from recognized sources. You need probabilistic analysis of rare but high-impact events, and understanding multi-regional weather patterns, how a swung in one area might affect another. Resilience metrics we look at include system-hardened investments, expected recovery time after an event, the availability of alternative supply paths, and the overall adaptive capacity of the grid.
And how do you put a dollar value on resilience?
The quantification approach is often framed as the sum of avoided outage costs using that VOLO we discussed earlier, plus the economic value of reduced recovery time. Faster recovery saves money and reduces hardship. It's about designing for a future we know will be more volatile.
Makes sense. Okay. Finally, our 7th benefit category ties transmission projects explicitly to broader policy objectives, state and federal policy goals. This is where the big picture really comes in, right?
It truly is. FERC Order 1920 explicitly requires planners to consider how a project supports clean energy goals, like state renewable portfolio standards. It encourages multi-state coordination on regional policy objectives. It brings in environmental justice considerations in infrastructure development, who benefits, who bears the burden, and it looks at how transmission facilitates regional economic development.
How do you quantify achieving policy goals? That seems less direct than, say, production cost savings.
It requires different methods. For renewable integration, the benefit can be calculated as the amount of renewable energy enabled by the transmission line, multiplied by the price of renewable energy credits, or RECs, plus the value of avoided emissions cost. You also quantify carbon emission avoidance directly. Economic development analysis looks at direct and indirect jobs created, increased tax revenue, impacts on gross domestic product. And for environmental justice, it's about analyzing equitable access to clean energy infrastructure and ensuring benefits are distributed fairly.
Okay, so those are the 7 benefits. Phew. What does this all mean for actually optimizing projects? Traditionally, maybe we looked at projects somewhat in isolation, but FERC Order 1920 seems to push toward a portfolio approach.
Absolutely. It's about optimizing across multiple potential projects and all 7 benefit types. The objectives are, well, first, maximizing the overall benefit-cost ratio for the portfolio. Second, mitigating risk through diversification. Don't put all your eggs in one basket. Third, capturing synergies where projects have complementary benefits. And fourth, always considering resource constraints, capital, labor, materials.
And it sounds like stakeholders are much more involved now.
Definitely.
Right.
Enhanced stakeholder integration is key. Bringing in state utility commissions, market participants, environmental groups, community representatives, economic development organizations, getting them involved much earlier and more deeply in the planning process.
And for you, the engineer listening, this means needing some serious analytical capabilities and software tools. Can you touch on what kind of tools are needed?
Sure. For those intensive 8,760-hour production cost simulations, you'll be using powerful platforms like Plexos, GridView, PowerWorld, ProMode. These are the industry workhorses. For reliability assessment, you need probabilistic tools like MARS, SERVM, or the reliability module in Plexos RA for those deep dives into system risk. And for market simulation, tools like Plexos again and PowerWorld Simulator are crucial for doing that competitive analysis we talked about. Each tool plays a specific, critical role.
So what's the bottom line for transmission engineers?
The bottom line is that the 7-benefit evaluation framework, it's more than just expanded analysis. It's a really fundamental shift toward holistic infrastructure planning. It considers all the value streams from transmission investments, not just reliability. Key implementation steps for utilities are pretty clear. You need to develop comprehensive data infrastructure to support all 7 benefit calculations. Invest in the right analytical tools and modeling capabilities. Modify existing planning processes to incorporate this framework. Enhance that stakeholder coordination we mentioned. And crucially, develop skills among engineering staff in areas like economic analysis, market simulation, and policy evaluation. It's a new era for grid planning.
It certainly sounds like a profound shift, this FERC Order 1927 benefit framework. It really is about seeing transmission projects not just as necessary cost centers, but as multifaceted value generators for our grid, our economy, and our society. This isn't just about building lines. It feels like it's about building a better, more resilient, and more economically efficient energy future.
And it definitely raises an important question for all of us, I think. How will accounting for these broader benefits, everything from fostering competition to enhancing resilience against extreme weather, how will that fundamentally change the types of projects we prioritize and ultimately build in the coming decades?
That's definitely food for thought, and a challenge we're now, hopefully, better equipped to tackle. Tomorrow, we'll actually expand on this, diving into how these 7 benefits must be evaluated across those 20-year planning horizons mandated by the order. We'll explore the scenario planning methodologies required to engineer for a future we can't entirely predict. This deep dive, remember, has been part of our week-long series featured in the PXRD newsletter on Substack, educating electric utility engineers on overhead and underground construction types. If you'd like to leave feedback or have any questions, feel free to reach out to us. I'm at alex.reed.power.podcast@gmail.com.
And I'm at emma.quinn.power.podcast@gmail.com. We'd love to hear from you.